Like always, in order for me to explain something, it's really a future topic. Everything is spread out in sections, but there's a lot of overlap. What is light? Light is an electromagnetic wave. So in physics we have the concept of fields. Our next unit is going to be over electrical and magnetic fields. We have basically an electric field. So it's just some imaginary field. We have this electrical field. And in three-dimensional space, we also have a 90-degree angle. It's hard to draw the magnetic field. So we'll learn this later on. A changing electrical field produces a magnetic field. A changing magnetic field produces an electrical field. So basically, a EM wave is a phenomenon where you have a changing electrical field that's producing a changing magnetic field that is thus producing a changing, it basically creates itself and it propagates out in the universe like this. As this electrical portion is changing, it's creating a magnetic portion that's changing that thus creates itself, basically, as it propagates on. So, EM wave. Let's see if I can get a picture. And they're at 90 degrees from each other. It's hard for me to draw in 3D, but we see that going up in the vertical axis, we have an electrical field, and then at 90 degrees offset of it is this magnetic field. If we look at an atom has a positively charged nucleus, and though this isn't really the case, we can think of the electron as orbiting around it. We know now this isn't what's really going on, but it's a good model. Physics is actually just a model anyway. Let me actually look up. Principle of least action. So going back to Snell's law, it follows the principle of least action. Basically, light will take the shortest possible path to go from point A to point B. B minimizes time. If you throw a baseball up in the air, or out in one direction, do you play baseball? And it gets to here, how does it go from point A to point B? Now, we could say it follows the laws of kinematics, F equals ma. And then gravitational forces, and work it out like that, and we can figure out that the path is going to be a parabola. We could also say that the ball randomly chooses the path that minimizes the kinetic energy minus the potential energy. It just randomly chooses this path for no reason. So it looks at all possible paths it could take, and just happens to choose the one that has the smallest Ke minus P value. Physics is just a model. there is no correct interpretation of it. You can look at it and be like, well, F equals ma makes sense to me. I know that for every force, you undergo an acceleration. I know gravitational force applies, but in actuality, it's just a model. Once you get into extreme physics, you realize that there is no good analogies anymore. It starts to break down to where you have to look at just purely mathematical. That's when you get into quantum mechanics. But around this electron is a electrical field. The closer you are to it, think of it like gravitational field. Well, you know gravitational field. The closer you are to the surface of Earth, the stronger the gravity is. As you get farther and farther away, that strength of the gravitational field is going to decrease, right? So if you were standing next to the Earth and somehow you're fixed point, you just choosing a point in space, and Earth is rotating around the sun, what is the gravitational field at this point doing? It's decreasing as Earth moves away from it. So we have a changing electrical field at every point. So as the electron goes around the nucleus, what's happening to the electrical field? It's changing. And a changing electrical field produces a changing magnetic field. And this, because the electron is constantly moving, it's producing a changing magnetic field. So what does electrons do as it goes around? And it produces, overall, an EM wave. I don't know if you know this, but you're actually glowing right now in light. You're glowing in light. You are giving off light. If I turn out all these lights in this room, you'd be very bright. What light are you actually glowing at? Well, can you see it? Is it visible?
Not the light I'm getting, no.
So it's not visible light. Do you remember all the light? We have radio. Then we have microwave. What comes after microwave? Infrared. Then visible. Then ultraviolet. Then X-ray. And gamma. So which one do you think you're glowing at? Yes. We have an infrared camera out there. If you turn out all the lights, it still sees the world just fine, because most things around room temperature, the rate at which the electrons are moving and the atoms are jiggling around, is giving off EM waves at infrared. So here's a question. Why does light slow down as it goes through a medium? What's in the medium? Electrons and protons, electric fields. And what happens whenever two waves interact? They interfere. They either constructively interfere or deconstructively interfere.
The internet is a very powerful tool, putting the knowledge of humanity at our very fingertips. However, the internet is also a source of misinformation. You can hear all sorts of explanations, stated authoritatively and with good intentions, but also utterly and totally wrong. So in this video, I thought I'd address a common one and give a correct explanation for why light slows down in water. Actually, that's just a catchy title. I want to tell you why light slows down in any transparent medium, certainly water, but also glass, plastic, and even air. If you ever took a physics class, you learned about the index of refraction of a material. The index of refraction is just a fancy term for how much light slows down in that material. The index of refraction, always written as little n, is a number greater than 1, and the speed of light in a material is just the speed of light in a vacuum divided by the index of refraction. I put a table here to give you a sense of how much light can slow down in common materials. This slowing down is the reason that objects look bent when stuck in water. It's because the path the light follows bends when it enters or exits water. It's the reason we can get pictures like this one here. And I should let you know that no physics teachers were harmed in shooting that photo. There's a ton of interesting phenomena I could show you that arises because of the index of refraction and the slowing of light, but I want to focus entirely on the slowing thing. So, to do that, let's look at this animation. So suppose you have a piece of glass with an index of refraction equal to 1.5. That means that light will travel at 2/3 the speed of light in the glass. If you shoot a laser at the glass, the light from the laser will travel at the speed of light until it hits the surface of the glass. When it hits the surface of the glass, the light will slow down to 2/3 its original speed, and it will change its direction. Once the light gets to the other side of the glass, it will emerge from the glass, change its direction, and move again at the speed of light. That's what happens. In addition, the light emerging from the glass will travel in exactly the same direction. Well, more precisely, in a path that is parallel to the direction of the incident light. The path is offset a smidge to the left, but the angles are the same. So that's what happens. It's been tested, and there's no debate on any of that. So now for the real question. Why does light slow down? And how can it speed up again when it leaves? There are two very common explanations that you find on the internet. Both of them are completely wrong. Let me tell you them first. The first one makes some kind of sense. It's wrong, remember, but it does make sense. It's the idea that light scatters off atoms as it passes through the glass. The light hits an atom and goes careening off at an angle, then hits another atom and careens off on a different angle. Light always travels at the speed of light between atoms. That process occurs again and again as the light passes through the glass. But let's focus on just these two scatters to see how the explanation goes. If we take away the atoms, we can see the important bits. There's the actual path traveled by the light in this scenario, which we can compare to the straight line path. If we straighten out the actual path, we see that it is longer than the straight line one. And if light travels at the speed of light in a vacuum between scatters, we see that it will take longer than it would if it went to straight line distance. Taking longer is another way of saying effectively going slower. And this is how some people explain the effective slower speed of light in glass. So how do we know it's wrong? Well, scattering isn't a precise process. Light can scatter in lots of directions. For instance, it could have scattered like we see here. This is a much more serious scatter with a much longer path, and consequently, light would effectively be much slower if this happened. Furthermore, there is no way to guarantee that the light would end up back traveling in the original direction. In fact, if light did what is being claimed, it wouldn't follow the path we observe. Instead, light would come out of glass with a range of velocities and a range of angles. This idea just doesn't work because it doesn't make correct predictions, so no good. The second wrong idea is that light is not scattered, but rather that it is absorbed and re-emitted by atoms. Between atoms, the light travels at the speed of light in a vacuum. The amount of time the atom takes to absorb and emit the light seems to slow the light down. You can see what I mean in this example here. The speed of the photons while moving is always the same, but the time taken during the absorption and emission makes the solid line take more time than the dashed one. This effectively makes light slower. Now, this idea, while sensible, is also wrong. Let's see why. The problem is that when an atom has been absorbed by a photon, it doesn't remember where the photon was coming from. And when it emits a photon, it can do in any direction. So what really would happen in the absorption and emission case is something more like this. The photon would be absorbed and re-emitted in a willy-nilly direction. In the end, the passage of light through the material would end up looking like this, which, well, isn't what we
These are both the two theories that are explanations I got in school. But you can clearly think about it, and it's wrong if you think about how the final result should be. It was, by the way, electrons, they can absorb photons and jump up in higher energy levels. That's more chemistry. But that does occur. Whenever something is absorbed, it's an electron jumping up to a higher energy level.
So, if neither of these ideas work, what does? First, I should say that these two ideas kind of have buried deep at the bottom of them the idea that light is a particle. However, the reason that light slows down in material is better illustrated if one embraces the idea of it being a wave. There are many properties of a wave, and most importantly, the wavelength. The wave oscillates up and down with a separation between peaks and a time between oscillations. A second important property is what we call superposition, which is just a fancy way to say that you can add them. And adding them is easy.
Did I mention superposition? So whenever I say they interfere and combine together, that's the property of superposition. Superposition is when you have two waves in the same place at the same time. They're interfering with each other. Superposition basically states that if you have two waves and they can overlap in the same position, so superposition, because you have multiple waves in the same spot, then the final wave is just the addition of both of them. A crest and a crest will add together, crest and a trough will kind of cancel each other out. Basically, superposition says that if two waves are at the same spot, the result is you just add them together like normal.
You just take the height of the two waves and add them together. If the two waves are lined up so the peaks are at the same place, the result is a single wave with a higher peak. If the wave is lined up so a peak corresponds to a trough, then the two waves cancel.
So we've only seen the scenario. Correct name on the word number. So we've only seen these two examples. What we haven't seen is what happens if we have two completely different waves. What happens if one has a lower frequency, shorter wavelength, or if they're not perfectly matched up.
And if one wave has a different wavelength than the other, you end up with a funny looking shape.
So if they have a different wavelength, you get this funny looking shape.
That's just how it works. It gets more interesting when one wave is moving at a different speed than the other one. The result is a different wave, but one that has a different speed than either of the two. That's super important. So let's just take a careful look at it.
And note that he's illustrating as one wave being completely still. Doesn't matter, it's relative to each other.
If we add the two top waves, which have different speeds, the bottom wave also moves, but slower. So let's get back to light moving through glass or water. Remember that light is a wave of electric fields. It oscillates with a characteristic wavelength and frequency. That wavelength depends on the color of light, with blue light being about 400 nanometers and red light being about 700. The numbers don't matter as much as that you remember that light is changing electric fields. Now, of course, glass is made of atoms, which are surrounded by electrons. Electrons have an electrical charge, and that charge feels a force from the oscillating field of light. Because it feels a force, the electrons move.
So when light passes by, so like a magnet, you can think of magnetism. If you have a north magnet getting closer to another magnet, it's going to apply a force to it. Because EM waves, electromagnetic waves, most of the time we just think about the electrical wave portion because the other one is just 90 degrees offset of it. Since we have a changing electrical field and electrons have an electrical field around them, EM waves will affect electrons and cause them to move. And when they move, it does a changing electrical field.
But moving electric charges also set up their own oscillating electric field. Said simply, the oscillating electric field of light makes electrons move, which makes a second oscillating electric field. And if you have two oscillating electric fields, That's two oscillating waves, and you can add them together just like we saw before. The net effect is that the two waves combine and make a single wave of oscillating electric fields. And that is the wave that moves through matter. And this is important, it moves at a slower speed than light does in a vacuum. This also explains something that many people were confused by. Most people were willing to accept that passing through glass slowed down light, but they were very puzzled about light speeding up when it left the glass. It seemed like it created energy, and well, that didn't make any sense. But now I hope it does. Before light hits the glass, it travels at the speed of light in a vacuum. When it passes through the glass, the light causes the electrons to move and generate a second wave that adds to the light. Light still moves at the speed of light in a vacuum, but the wave from the electrons move at a different speed, and the combined wave moves slower than light would if the atoms weren't there. Then, when light leaves the glass, there are no atoms around to make electric fields to add to light, and then light speeds along at the preferred vacuum speed. So that's it. Light effectively travels slower through material because when it is in material, it generates a second wave that combines with a light, and the combined new wave moves slower than the familiar speed of light. Ta-da! All right, so tell everyone.
So I hope that made sense to you. So basically, as light travels through a material, it causes the electrons to move. A moving electron causes a change in electrical field, which creates a new EM wave, which combines with the original wave causing it, and we get a net effect of the superposition of this wave moving through. Which can kind of tell you exactly which materials are slower for light to move through. What do you think? So how do you think different materials? What does it depend on? Like, for example, water versus glass. We know water is 1.33, glass is 1.5, is the index of refraction. So it goes slower in glass because so it goes the fastest in air. Air has, what's the difference between air and water? Well, no. I mean, like, why does it go faster in air than does water? There's still electrons in air. So, density. The more dense your electrons are packed together, the more effect, the more wiggling's going to go on, and the more the light will slow down. So, diamond is very dense and hard. Let me see if I can look that up. So, density of water is 1, so, or 1,000 kilograms per cubic. Density of glass is 2.5. Density of diamond is 3.5. So as the density increases, that usually affects, not always, because it's slightly more complicated than that. Alright, that finishes refraction and reflection. Have you been working on the homework?
Yes, I've been working on it.
So now let's do diffraction. So then, let's say that we have incoming light. These lines represent the crest. So incoming light. And I have a barrier. And I have 2 slits. This is called the double slit experiment. So I have 2 slits, 2 openings this light can go through. So as light reaches these splits, what's it going to do? Like this wall is going to block it off, so it can't go through the wall. The two slits. So it's going to go through the two slits. And also, light tends to spread out as it moves. And again, every line represents a crest. What are you seeing here? So we're seeing superposition or interference. Let's say we have a wall. If you were to imagine this as throwing baseballs, if you're throwing a lot of baseballs toward this wall, and we have a projector screen over here, you would see that a lot of impacts will be right here and right here, right? But light is a wave that spreads out and can have interference with itself. What we see is a very bright spot in the middle. And we see another bright spot, another bright spot, another one like this. What's happening is, let me illustrate it. Is we have a light coming in, hitting right here. And let's see if I can draw this correctly. So I have two troughs hitting the same point at the same time. That means they're going to constructively interfere. The amplitude's going to go up, so we get a bright spot. It's traveling the same distance, right? So this light traveled the same distance, so they should meet up at the same point. As soon as a crest hits this point, we should see that it should continue to propagate. Now let's look at it. Like this. So we see a big bright spot right here. Now let's look at right here. This light went and traveled like this. And this light traveled like this. It took a longer bit of time, so it's not going to end up hitting in the same spot. I can see a crest hit right here and a trough hit right there. Deconstructive, and we don't see any light. We can work through a lot of algebra. And also, sine wave repeats itself. So what we're going to see is a series of bright dots and a series of dark spots and a series of bright spots. That matches up with this angle, depending on where it is. If I plot the intensity, how bright it is on the wall, obviously the farther away it is, the darker it gets. But this representing brightness, we see a very bright spot right in here, another bright spot right here, another bright spot here, like this, with dark spots in it. It looks like this when we're set out. And let me look up the equation. Diffraction equation. So, we have some distance here. Nope, never mind. We have some distance here between the slits. I'll call it D. Let me just rewrite this. So I have some distance here between the slits. I have a wall on the other side. I'm going to draw an imaginary line that is perpendicular between them. And so we have a bright spot here. I'll call this n equals 0. I have a bright spot here. And these only work if the slits are very close together. So approximating in the point in between them, I'm going to call this theta. And this will be n equals 1, n equals 2, n equals -1, n equals -2. Then the relationship is d times sine of theta is equal to n times lambda. So this is the distance between slits. This is the diffraction angle. This is the order number for maximum. And we call a maximum for brightnesses. So these things are called maximums, while these dark patches are called minimums. So minimum dark spots. Maximums are bright spots. And this is the wavelength, which is also one of the reasons why lasers and stuff are all given in wavelengths and not frequency. Even though frequency is the better number to use, this equation depends on wavelength. Because we want, so interference depends on when the wavelengths match. Basically, you have this written? So, in order for them to have constructive interference, you have to have the same number of wavelengths. So, basically we have some, I'll call this A, some distance between the slit and the wall. Right here, we want some number of wavelengths, and this could be a wavelength plus 1. Then they'll have a crest and a crest will overlap. Right? If you move it over by 1 wavelength, it looks the exact same. So this is the equation on how it's defined. And let's use it. Let's see if I can find it. Looking for a broken CD. What would I have done with a broken CD? I break one like every year. I just continue breaking it. What's the smallest distance you ever measured?
I mean, in the egg shop, I've measured like 8 or 16.
That's very large.
Yeah.
An eighth of a minute? 16th of a minute? Have you not ever measured micrometers?
No.
You have a cart right here, but just look at something. I don't remember. I'm gonna call my family. Figure out whatever that means. A broken CD. Do you know how a CD works?
Not really. I just put it in and
So, I have a broken CD. More specifically, I've removed the shiny bit off of it. So, do you know how a record player works? So, inside of this CD is a spiral. It etches into it little tiny holes. And it goes around the entire circumference of this, goes in the entire round. And then it starts on the next line. And it's in binary. But we kind of have basically slits. And we have some distance right here between the slits. This is known as a diffraction grating. Diffraction grating is just multiple slits. It doesn't matter if you have 2 or if you have 100 slits, it makes no difference. So if you have instead something like this, where multiple slits makes no difference to it. It's still going to work out the exact same. It's still going to use the same equation. But we can figure out the distance between these slits. So, get a new piece of paper. If I shine my laser through the CD, through my diffraction grating, and I'm going to blow it up, we're going to have multiple different slits that are some distance D, and then I'm going to have a wall. And from the distance from my CD to the wall, I'm going to call A. And we're going to get a dark spot that is going to correspond to n equals 0. And then I'm going to have next to it a bright spot. This will be your n equals 1. And it will be some distance. So some distance I'll call B. And we're going to get an angle. Theta. And we know that n1, or n equals 1. So we know our equation is d sine theta is equal to n times lambda. And we can do this when this will be n equals 2. And I get another angle corresponding to n equals 2. But we're going to choose n equals 1. It doesn't matter. My laser is 532 nanometers, or 532 times 10 to the negative 9 meters. All we need to do now is measure an A and measure a B. So let's do that on the board. Grab more of them. Diffraction. We did it in your class too. So we got a laser pointer. And as soon as it goes through a diffraction grating or slips, it is going to produce. We see it like that. Let me rotate this and see if I can. Alright, I see you can get the one, but it's because it's hitting the book. I want um, close enough. Last year I forgot how I did this. I had it perfectly wrong. Which means I need. How much time do we have? I think we'll have to do this. I really want to do this. So how far away? You have to measure this distance. So we need to measure this distance. We can do it on the wall. I'll figure it out this time. But we're going to get an incredibly small number. And then we'll look up the actual number and see how close we got to. Let me show you another diffraction grating real quick. So I have a pair of glasses that have a diffraction grating like this. So we have multiple vertical slits, multiple horizontal slits. What do you think the dot patterns will look like? So, ordinary light. So everywhere you see a bright spot is constructive interference. Everywhere you don't see light is all deconstructive interference. And as you get farther away from the central maximum, it gets darker and darker and darker. There's theoretically an infinite number of dots. Well, realistically, there is a limit to how many photons can be generated, but even like that. This works also with light, but lights are going to have different frequencies. Put this on and look at the lights. So now we have, this was just showing interference between green and green. That's showing interference between different colors, which separate them out, kind of like a prism does. Those lights only produce certain colors. But on Monday, we'll do this experiment.